In this video, we're going to be looking at collision theory and rate of reactions. This is one of the main ideas behind a study called kinematics. Collision theory. Collision theory states that in order for a reaction to occur, reactants must collide with each other, so they actually must come in contact. Now, they also must come in contact and they must collide with the correct orientation, so the molecules need to be orientated in the correct way, and they also need to collide with enough energy. The energy needed for a successful reaction to occur is actually called the activation energy. If these two things are met, the correct orientation and enough energy, then the collision will result in a product being produced. So it will result in the reaction moving forward. Here's an example of a correct orientation. So here we have 4 different ways that reactants could collide. As we can see, only one of these collisions results in the correct orientation. So here we have the white sphere attached to the green sphere, probably saying that that white sphere is hydrogen, needs to be able to collide right where that double bond is between the 2 carbons. Any other collision will not result in the correct orientation and will not result in the reactants actually colliding to produce the product. They need to collide in a certain way. So that is one of the criteria for having that collision theory. The second one is activation energy. And the idea behind activation energy is that the reactants need to collide with enough energy that they will actually break bonds. The amount of energy that they need to collide with varies between different reactions. So it really depends on what reaction is taking place. So some reactions have higher activation energies, some have lower. The higher the activation energy is, the more energy those particles need to collide with. So if they don't collide with enough energy, they're just going to bounce apart from each other. Think of 2 billiard balls. But if they collide with enough energy, they're going to be able to break bonds and form their reactants. Now, reaction rates. Reaction rate can be defined as how fast reactants turn into products. Naturally occurring reactions have different rates of reaction, so they don't all react with the same rate. For example, here I have a picture of a diamond in a rock. Forming diamonds from another carbon source is an extremely slow reaction that takes thousands and thousands of years. But that is a reaction, but notice that it is a very slow reaction. On the other hand, burning a match, as you guys have probably done, and we actually have done in class, is a fast reaction. It happens very quickly, and that reaction happens almost instantaneously if you think of how quickly that flame occurs. So as we can see, the rate of the reaction can really vary depending on the reaction that's taking place. Depending on the reaction, we could actually change the rate of the reaction in several different ways. So a lot of the time in a lab or something like that, we want to be able to make the reaction occur quickly. So there are different ways that we can do that. Keep it in mind that that's the idea behind collision theory and how that works. So the first way of increasing the rate of the reaction is to increase the concentration of reactants. So by adding more reactants, we increase the number of particles in the reaction. By increasing the number of particles, what will happen is that more collisions will occur. If more collisions occur, that means that there will possibly be more successful collisions. Therefore, more collisions mean that the reaction will happen faster. So here I have a diagram at the bottom. Again, more molecules, more reactants mean that there will be more collisions. More collisions means that our rate of reaction will increase. So the first way is increasing the concentration of reactants. The second way is to increase the temperature. Increasing temperature means that substances are moving faster. We've talked about temperature before. Remember that temperature is directly related to the kinetic energy. So the higher the temperature, the higher or the faster those molecules are moving. If they are moving faster, 2 things will occur. They're moving faster, more collisions will happen because they're moving around faster so they can be able to collide with different molecules faster. But as they're also colliding and they're colliding with faster speeds, they're actually going to be colliding with more energy. So if that happens, if they both collide more frequently and collide with more energy, that'll increase the rate of the reaction because there's more successful collisions, and more likely that they will collide with enough energy for the reaction to occur. So increasing temperature actually works on two fronts. Surface area. By increasing the surface area of a substance, we expose more molecules that are available to react. When I think of this idea of dissolving granulated sugar versus sugar cubes. As we see in the picture that I have down here, by increasing our surface area, it allows more reactants to collide. And it kind of opens up the reactant so that molecules that maybe were inside or towards the middle now are exposed and able to collide. So we are increasing the number of collisions that could happen. The last thing that we're going to be talking about is adding a catalyst. A catalyst is a substance that is added to a reaction. It doesn't get consumed or anything like that, but what it does do is that it lowers that activation energy. So the energy that is needed for the reaction to occur. By lowering the activation energy, more collisions will collide with enough energy to react. So the main thing when we're talking about collisions and activation energy is that a lot of the times they won't collide with enough energy. So if we lower that activation energy, that means that more molecules will collide with enough energy because we've lowered it. And if they collide with enough energy, they will then turn into products. As we see down here at the bottom of the screen, we have some energy diagrams that we looked at last week and the week before. We're actually going to be using these energy diagrams to do a few more calculations and kind of look at this. But as you can see on this diagram, the activation energy is the distance between the reactants and the top of the peak. That's the energy that needs to be inputted, or those molecules need to collide in order for the reaction to occur. So notice that really tall peak in blue. By adding a catalyst, we lower that peak. So now the energy barrier is lower and more reactants will be able to collide. Right here, I have a video that I show every single year that I'm going to go ahead and play at the end of this, which I think is a really great way to sum up kind of this idea of reaction rates and things that affect them.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased and each particle has an exposed surface that can react. Fifth and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.